Welcome to this video where we shall be looking at the state observer design as the second method of controller design in state variable methods. Our topic is state observer design. Previously, in the pole placement design, it was assumed that all the state variables are available for measurement and feedback. This will not always be the case, because in some cases, not all the state variables are available for measurement and feedback. Sometimes it becomes very difficult to measure some of the state variables. Sometimes the sensors for measurement of those state variables may be very expensive. And the only way to be able to determine the state variables that are unmeasurable is to estimate such state variables from the measured values of the output and the input of the given system. And therefore, in state observer design, we aim to estimate the unmeasurable state variables based on the measurement of the output and control variables. If a state observer is going to estimate all the state variables, regardless of whether some of them are measurable, then that state observer is called a full order state observer. If it measures only the state variables which are not measurable, it is called a minimum order state observer. The necessary and sufficient condition for observer design is that the system must be completely state observable. In other words, before we design a system in state observer, or before we design a controller in state observer, we must evaluate the observability condition of that system. And by observability, we basically determine the observability matrix N, which is given by C, CA, all the way to CA, N minus 1. And if we evaluate the determinant of N, and we notice that this is non-zero, then the system will be said to be observable. And a state observer can be designed for such a system. The system will be defined in state variable method, or will be modeled using the state space model. And then we proceed to design a state observer based on the required locations of the poles for our given system. Suppose our system is defined by the equation or the state equation, x of t derivative is equals to ax of t plus bu of t, and the output equation is y of t is cx of t. We model this system in block diagram as follows. We have modeled this before. So our system will have the input u of t getting into matrix B, then a summer. We feed back x of t having passed through A. This is our x of t derivative. We have an integrator to get back our x of t, feed back into the system, and then we pass x of t through C to get our output y of t. And this has been the block diagram representation of the state space model of any given system. We would wish to estimate the unmeasurable state variables of the system based on the output of the system as well as the input to our given system. Therefore, we develop a controller based on the estimated values of the states as follows. So we still adopt the block diagram, and we can modify these as follows. So this is the modified controller. This is the measured output of the system. This is the input or the control variable for our given system. Then at this point, then this will be estimated values of the derivatives of the states. To indicate that the estimated values, we indicate with a tilde, and therefore this will be the estimated states of the system. And from this, we notice then this output will be an estimated output of our given system. So we modify our controller such that we have a feedback matrix G multiplied by the difference between the output and the estimated output of the system to constitute the estimated derivative of the states for our given system. We call this equation 1 and this equation 2. From the block diagram representation of the designed controller, we can observe then that the estimated states of the system derivative will be equal to, the estimated states of the derivative will be equal to A multiplied by the estimated states, this loop, and then plus G multiplied by Y minus Y estimated plus BU of T. Okay, so this is Y minus Y. Then we add to G. Then we add U of T being multiplied by B. Then we also notice that the estimated value of the output will be equal to C multiplied by the estimated states of the system. We can call this equation 3 and this equation 4. In equation 3, if we substitute for Y and Y estimated, then we can write equation 3 as follows. The derivative of the state estimated will be AX estimated plus G. Then instead of Y minus Y estimated, that will give us C into X estimated, X minus X estimated. So this will be X minus the estimated value of X plus BU of T. And we can call this equation 5. Now, if we take equation 1, and we subtract equation 5, if we take equation 1 and subtract equation 5, on the left-hand side of our equation, I'll have X derivative minus x estimated derivative. So this is the left-hand side of equation 1 minus the left-hand side of equation 5 will give us then ax of t minus this. So that means we'll have a, which is common, into x minus x estimated minus gc into x minus x estimated. You notice the bu and bu will cancel out, and this we can call equation 6. If we take equation 2, we subtract equation 4. We take equation 2, subtract equation 4, we'll have y minus y estimated will be equal to c into x minus x estimated. We can call this equation 7. From equation 6 and 7, we can define new variables as follows: x derivative minus x estimated derivative as x derivative hat, then y minus y estimated to be y hat, and therefore x minus x estimated will be x hat. If we do so, then we can write equations 6 and 7 as follows. We can write equation 6 and 7 as follows: x derivative hat will be equal to x derivative hat will be ax hat minus gcx hat. You can write that as ax hat minus gcx hat, which we can write as x derivative hat to be a into, it will be a minus gc, a minus gc into x hat. Call this equation 8. Then from equation 7, we will have y hat to be c x hat. We can write y hat to be c x hat, and you can call this equation 9. From equation 8 and 9, we notice then that our system's characteristic equation, the characteristic equation of our system, will be obtained from the characteristic equation will be obtained from Si minus A plus GC determinant. That will be our characteristic equation obtained from equation 8. The design problem is to determine a feedback gain matrix G that will ensure that our characteristic equation is of this format, or the location of the poles of the system are at the desired positions for the given controller. And therefore, the design problem will to determine a feedback gain matrix G that is able to ensure that the eigenvalues of the characteristic equation are located at the desired location. The matrix G will be an n by 1 matrix. It will be an n by 1 matrix defined by G1, G2, all the way to Gn. It will be an n by 1 matrix defined by G1, G2, all the way to Gn. To determine the transformation matrix G, or to determine the feedback gain matrix G, we can use 3 methods, just like in the pole placement design. And therefore, the first method will be the direct substitution method. The direct substitution method. In the direct substitution method, if the desired location of the poles are defined by mu1, mu2, all the way to mu_n, we can obtain the desired characteristic equation as S minus mu1 into S minus mu2 all the way into S minus mu n is equals to 0. From the designed controller, our characteristic equation is given by Si minus A plus GC determinant is equals to 0. So this is the characteristic equation with the controller, and then this is the characteristic equation based on the desired location of the poles. We will choose G to be the matrix G1, G2, all the way to Gn, depending on the order of the system. And by equating the two equations, which are the characteristic equation of the system, we can solve for G by equating Si minus A plus GC determinant is equals to S minus mu1 into S minus mu2 all the way into S minus mu n. And through this, then we can solve for the matrix G using the direct substitution method. The second method, or method number 2, is what we call the Ackermann's formula, similar to the Ackermann's formula in the pole placement design, the Ackermann's formula. By definition, the feedback gain matrix G will be given by G is equal to phi of A multiplied by N inverse multiplied by 0, 0, all the way to 1. This will be the definition of the Ackermann's formula for the determination of the feedback gain matrix G, where N is the observability matrix defined by C, CA, all the way to CA power N minus 1. So N is the observability matrix that we determine when we are testing the observability of the matrix. And our phi A is obtained from the desired characteristic equation of the system when expanded as a polynomial in S as follows. If the desired characteristic equation is S minus mu1 into S minus mu2 all the way into S minus mu n, when expanded, it will be a polynomial in S written as S power n plus alpha 1 S power n minus 1 plus alpha 2 S power n minus 2 all the way up to alpha n minus 1s plus alpha n is equals to 0. This is the desired characteristic equation, which is a polynomial in S with the coefficients alpha I. Our phi of A will be obtained by substituting for S is equals to A into the desired characteristic equation, such that this will be A power n plus alpha 1 A power n minus 1 plus alpha 2 A power n minus 2 plus all the way up to alpha n minus 1A plus alpha n I, and that is our phi of A. Then from that, then we can determine our feedback gain matrix G by multiplying phi of A, n inverse multiplied by the matrix. The last matrix is a matrix whose terms or whose elements are 0, apart from the last term, which is 1. And therefore, depending again on the order of the system, this matrix will have the first terms being 0 and the last term being 1 for our final matrix. And that is the Ackermann's formula for the determination of the feedback gain matrix K. Lastly, number 3 is using the transformation matrix method. Again, similar to what we covered in the pole placement design, the transformation matrix method. In the transformation matrix method, 1, we will have evaluated the controllability of the system, the observability of the system first before we determine the observability or the feedback gain matrix G. Once we confirm that the system is observable, then we determine the characteristic equation of matrix A. Si minus A determinant is equals to 0. We determine that characteristic equation, and we expand these into a polynomial in S with the coefficients AI as follows. This is the polynomial in S as S power n plus A1 S power n minus 1 plus A2 S power n minus 2 plus all the way up to an minus 1 s plus an is equals to 0. So we expand for the characteristic equation of the matrix A as Si minus A determinant is equals to 0 to obtain a polynomial in S with the coefficients Ai. Number 2, we determine the transformation matrix Q. We determine a transformation matrix Q that is able to transform the system state space model into observable canonical form. We determine the transformation matrix Q that is able to transform the system state space model into observable canonical form. If the system is already in observable canonical form, then our Q will be equal to I, an identity matrix of the same order as the order of the system. Otherwise, if the system is not in observable canonical form, then Q will be equal to W multiplied by N, where N is the observability matrix. So N is the observability matrix we've been using as C, CA, all the way to CAN minus 1. And W is a matrix that is obtained from the coefficients of the characteristic equation of the matrix A, is the equation as follows. So the first row will be a row of AN minus 1, AN minus 2, and then all the way to A1, 1. Then we'll have AN minus 2, AN minus 3, 1, 0. Then we'll have A1, 1, 0, 0. This will give us 1, 0, 0, 0. Similar to that is the matrix W as discussed under the pole placement design. So that will be our matrix W, and the transformation matrix Q will be obtained by the product of W and N. Once we have the transformation matrix W, number 3, we determine the desired characteristic equation of the system based on the location of the poles of the system as S minus mu1 into S minus mu2 all the way into S minus mu n is equals to 0 if mu1, mu2 all the way to mu n are the desired location of the poles, which will be a polynomial in S with alpha I as the coefficients as S power n plus alpha 1 S power n minus 1 plus alpha 2 into S power n minus 2 plus all the way up to alpha n minus 1 S plus alpha n is equals to 0. Next, we determine our matrix G to be equal to Q inverse multiplied by alpha n minus an, alpha n minus 1 minus an minus 1, all the way up to alpha 1 minus a1. We multiply that with an n by 1 matrix given by alpha n minus an, alpha n minus 1 minus an minus 1, all the way to alpha 1 minus a1. And this is the feedback gain matrix G using the transformation matrix Q that is able to transform the system state space model into observable canonical form. And those are the methods of determination of the feedback gain matrix G, the direct substitution method, the Ackermann's formula, and the transformation matrix method. In my next video, I will adopt a problem in observer design and obtain the solution for G using the 3 methods. Otherwise, that is the end of my presentation. Thank you for watching the video.